Okay, I'd like to talk about something different this time. So I like to talk about like uh, global. Hopefully, I can write here. Uh, Global polling. So it's just polling, but it's like polling the entire layer. So I take two examples here. One example is PointNet. Um, so PointNet is like the objective is that you have some cloud points like some I don't have an image here, but like cloud points. Maybe this is cloud points of a maybe a cloud points of a can, and then it's trying to recognize like okay, this is a can here, and maybe I should have like something more complicated. Let's say if I have a cloud points of a car now, the cloud points there like also contain like there's wheels here and there's cars at the body of the car, the points that correspond to the body of the car. So maybe the wheel will be different colors. uh, so the objective there is trying to uh, recognize both the object of the car point, like what the car point is describing, and at the same time like for each point like uh, which what's the semantic information of that point, like basically do a semantic segmentation of the car points. For example, like whether the point is belong to the wheel or like belong to the body of the car. So so one important property for car points is that like unlike, for example, if we are working on images, then the usually the data will be like arranged orderly, like maybe like it's in a just scan horizontally like row by row and so on. So but for car points there no particular order is, and it can be all scattered around. So and I mean it can be like well, I mean it can be all scattered around more clearly I should say, like for example I can have like this is the first point, and then the second point can jump to here, and then the third point jump back to here, and so on and so forth. uh, So in this case, it probably does not make sense to do like, for example, like something like CNN, because if you do a convolution, like for example, if you arrange these points into a vector, and if I do 1D convolution, basically when you do convolution, you're assuming that like you can strip kind of like reduce the size of the filter just because like all the information regarding the target pixel or target point at this moment will be covered by the neighborhood of the filter. Basically, like for all the points that covered by the filter should should be like highly correlated with to the point, and those that outside the filter is like not so correlated. But in this case, because I it just hop around, like you cannot ensure, for example, if this is the first point, this is the second point, and this is the third point, and so on. So the second point, the first and the third point does not need to be very much correlated. So then the idea like for this point net is that like okay it use this kind of like okay the key idea is it use this kind of global polling. So basically like it will kind of process each point individually until like it get pretty much um near the end, I guess. Then we'll just do a global polling to, in this case, it's a mass polling. So maybe like I start from like here, like I have this n points and data points and points in the point count here. And then because it's like in 3 dimensional, so it's like n by 3, the points. Now then you will do go for an input transform. I will describe in more detail later on here, but it's just basically for each point it's going to do a transform. So it would be just a rotation. Maybe there's some it can be some scaling as well in different dimension, and rotation, scaling, and translation, and so on. So then I basically the objective here is like to do some alignment, right? You want to have like no matter like for example the point originally in this orientation like as a car, you want to always arrange into the standard canonical orientation like this. Um, so hopefully like this input transform will be able to do that. Then afterward, like for each individual transform point, we just do a MLP, like just a fully connected layer, but doing it separately. But like for each of the point, they will have use the same filter, so the coefficient will be shared. Then afterward, we'll get to a uh, basically like we'll extend the length of the feature like to 64. So I have n by 64 of them. Then we can do another transform. You can think of like another alignment, but in the feature space. And then I will do MLP like with like different kind of like lengthen it like from like 64 to 128 to 1024. And again, like this will be done like point by point like separately. Afterward, like here we'll do a mass pooling. Here's the part that like we'll just group all the points together. But because the points are arranged not in an orderly manner, so the most intelligent thing we can do is just simply polling. So we do a global polling. In this case, we use a mass polling, and we get a global feature, basically, a global feature of a length 1024. And then we will use that to classify the class, whether this is a car or a can or something like that. Um, and it will be done like for another MLP as well. And so the careful thing of the pointer is that like uh here like we can pack in this global feature like along with this the intermediate local feature together to get this combined feature, and we use that like to do point by point classification. So then for each point we will do a semantic segmentation, whether this is a again is a point that belong to the wheel or like a point belong to the windows or like a point belong to the body of the car, say. Um, and then yeah, and then afterward, like you classify like each point. And actually, basically, it has an intermediate step also. Like you have run through several MLP, you get this is a point feature. So, for example, this feature can be used for other application, but uh, this is a kind of like we group this local and global feature together, and then we do some, you can think of some distillation or like from some compression to get point features. It's, you can think of this like feature like in SIF, like you can similar to SIF feature, and at least you can be used like similar to SIF feature, and then eventually like you use this feature to do classification like for each of the also like which segmentation semantic uh, classes the fossil belong to. So that's for PointNet. So that's one application for like global polling like here. So let's look at another application. Okay, actually I skipped this one here. I didn't finish the PointNet. Yes, the transform here, basically this transform, what has been done is like we learn this transform and we multiply this transform, right? So this transform itself will be adaptive. Basically, like it will depend on the input. So we're trying to train a network so that given the n data points here, trying to learn the transform, basically hopefully we'll learn the transform to align whatever like input image, sorry, input cow point to a canonical pose, say. And what I think this is actually extracted from the blog, it's not extracted from the paper. I assume that this is a figure like is kind of drawn correctly. Uh, so, but it's, you see, like it's pretty simple. It's just one for like several MLP. This is like all like done separately. Again, like each of these um, are done point by point, but they have shared coefficient for the filters. And then eventually, again, I do a mass polling here. So similar to this step here. Uh, and this basically, yeah, summarize all this information. And then I do more like kind of like fully connected layer, and then eventually to get the get the matrix here. So get basically 1 by 9, and then we shift to 3 by 3. So of course, I hear the feature transform for this one will be the same, but just this one, the last step here, instead of like the filter is 256 by 9, so we have output like the size would be like 64 by 64. This would be like 2 to the what's that? It's 2 to the 6 and 2 to the 6 or 2 to the 12, something like. So 2 to the 12 is a 496 or something like 1496. Yeah. So this is PointNet. Like that's all I want to talk about PointNet. So another application like for global polling is like this known as SENet. So SENet is a stand for like squeeze and excitation. So it turns out this one is the winner of like 2017 image-led competition. So this very famous competition, like in the categories, image classification is the winner for the image classification. It pushed down the previous like error rate, like top 5 error rate, from 2.991 to 2.2 something. I forgot 2.225, or I had to look at the number again. I forgot. 2.251, yeah. So it is a quite a significant gain. And the idea is very simple, actually. The idea, and also it's very generic. You can use that like in any module, basically, in any electrode module. As long as you have a feature, let's say like you have like some feature in the networks, and you have C channels there, and each of the, I mean like C different channels, and you can, for each of the channel, you can have different dimensions. In this case, an example is just a 2D per channel. So therefore, like in this case, like each channel, for each channel, like the dimension is h by w. Apparently, you can apply it anywhere else as well. So for example, you can apply in 3D and also 1D and so on. If, for example, if it's 1D, it would be like C by H, like maybe C by H. And for each of the channel, what is done is like just first you start with a squeezing. This squeezing, like okay, maybe use that back. So squeezing is simply do a average polling. So you summarize. Maybe I give the high level idea first. Like the high level idea is basically we want to learn the weight to scale like the significance of each of the channels. So given the parameters like at this moment, or given the the representation at this moment, so for each of the channel may have different weights. So we want to learn the appropriate weights for them. So basically we'll learn a scaling factor. So we will be the scaling like factor that will have a length C here. And then after we learn that, we just scale like for each of the different channel, we just scale by that value. For example, like for the first channel here, it was scaled by this command, sorry, this amount here, right? So therefore, like you see, like that this the entire channel is have this color and so on. And I'm learning that it's very simple. Basically, like the first step, as I said, like is just squeezing that. Like so, for the entire channel, we just average out all the values in that channel. So we just do average polling. So to get a tens of 1 by 1 by C, or like just a vector of length C. So afterward, like we'll do this excitation function to estimate the weight for each of the channel. This can be implemented very easily. For example, like what's suggested in the paper is simply to do several fully connected, basically fully connected layer, evaluate a fully connected layer. It's just 2-layer MLP. and then end it with a sigmoid. Um, and then like that is what, okay, what we computed the weight. So once we computed the weight, as I mentioned earlier, we'll just say scale each of the channel with the corresponding weights, and that's it. So apparently you can apply it in anywhere. And for example, like you can apply in inception network. For example, the original inception layer is just an inception here, but at the end, like we have the representation from the inception. Now you have this branch here trying to learn the weights here, and then after you learn it, you just scale it like the output of this inception layer, so you get a new uh, weighted output, weighted representation. Or you can add it in Westlet, then we get a SE Westlet module. So it's like very similar. After you have in the output of the residual, we can pass through another like this squeezing and excitation module to learn the weights, and then we'll scale the output of the residual network, and that's it basically. And and this is really nice. It's very simple. You can use it anywhere, everywhere, and it it did give you a significant gain, uh, at least for this image classification application. So that's it. Actually, that's all I want to talk about today. Okay, thank you for your attention.